Hello, everyone. Welcome to section 10.3. In this section, we're going to keep talking about systems of linear equations, but now we're going to start talking about matrices and how we can work with those to solve systems of linear equations and how we can sort of start working with those as like a shorthand because they can be a little bit faster to work with as opposed to trying to work with the equations directly. So to start off, when we were solving systems of linear equations, we were really just focused on working with the coefficients, right? Like we cared what the variable was, but really we were working with the coefficients to zero things out. So if we have a system of linear equations, for example, something that might look like 2x minus 3y plus maybe 1/2 z equals 5, and maybe like an x plus 4z equals 9, and maybe like a 2x minus y equals 0. So if we have a system of linear equations like this, we can go ahead and write down the corresponding matrix. And the matrix just kind of records the coefficients in front of the variables. So the corresponding matrix for this system of equations. So to start off, we see a 2 in front of the x here in the first equation. So we're going to put a 2 in the first slot there in the first row in the first column. And then we see that there's a minus 3y. So there's going to be a minus 3 in this slot right here. And then we see that we have a 1/2 z. So that 1/2 goes right here in this slot. And then lastly, we see we've got a 5 on the other side of the equals. We want to record that too. That's good information. So we're going to put a 5 there. So that's the first row of the matrix corresponding to this system of linear equations. Let's go ahead and fill out the rest of it. It's good practice. So for the next line, we have an x. There's no coefficient written in front of the x, but secretly there's a 1. So we're going to put a 1 here in this entry. And then there's no y variable in the second equation. That's because secretly it's 0 times y. So in that case, we put a 0 for the y entry. And then there's a 4 in front of the z, so we'll put a 4 here. And then there's a 9. So we'll put a 9 right there. And then for the last row, the last equation, we've got a 2 in front of the x, so we'll put a 2. And then minus y, so that's a -1. We'll put a -1 here. There's no z, so secretly it's 0 times 0. So we'll put a 0 there. And then the other side of the equal sign also is a 0. So we'll put a 0 right there. So whenever you see a matrix like this, that corresponds to a system of linear equations. Sometimes this is what's called an augmented matrix. Each of the columns correspond to a variable. So this is like the x column, this is the y column, and this is the z column. And then the last one is like what the number is on the other side of the equal sign. Sometimes, so this is an augmented matrix. It's called augmented because we have the numbers that were on the other side of the equal sign. Sometimes when people write augmented matrices, they have like a little dashed or dotted line in between the coefficients of the variables and the numbers that were on the other side of the equal sign. But your book doesn't use the dashed line, so I won't either. But if you ever see that, that's just what that means. Okay, and so you notice that if we started with this matrix, we can go back and we can recover the system of linear equations, right? We just say, oh, there's a 2 in the x slot for the first row, so we put a 2 in front of the x, and there's a -3 in the first row in the y slot, so we put a -3y, and then a 1/2 z equals 5. So we can recover the system of linear equations. So we can kind of go back and forth between these, and that idea is important. So before we start talking about solving systems of linear equations with matrices, let's talk about some properties of matrices. So the size of matrix matrix is called its dimension. And it's written as like row times, so x column So as the number of rows times the number of columns. So for example, if we had a matrix like 2, 1, 0, -3, 1/2, 4, 0, 0, 2, this has 3 rows and 3 columns. So this is what we would call a 3 by 3 matrix. Okay, maybe like a different example, if we had something like 1, 3, 5, 9. This is just one row, but it's still a matrix. So it's got 1 row and 4 columns, and this would be called a 1 by 4 matrix. So the dimension of the matrix is the number of rows, x, the number of columns. Okay, so let's go ahead and take a look at solving the system of linear equations with the matrix. We're going to go ahead and do this example side by side. So on one side, I'm going to do it solving it with the equations as usual. And then on the other side, we're going to do it with the matrix. And we're going to see that they mirror each other. I think they do exactly the same thing, so that we can get really a sense that when we're solving systems with matrices, we're just doing the same thing that we did before, but without writing down the variables. So let's take a look at that. Let's say we wanted to solve a system that looks like this. Do x minus y plus 3z equals 4. And then we'd be like an x plus 2y minus 2z equals 10. And then maybe like a 3x minus y plus 5z equals 14. Okay, and then we're going to go ahead and on this side, let's do the corresponding matrix. So we have a 1 in front of the x, and then a -1, and then a 3 and a 4. So that's the first equation recorded, the first row. And then for the next one, we have a 1, 2, -2, 10. And then for the last one, we have a 3, -1, 5, 14. Okay, so now let's go ahead and solve this as we would normally. So to start off, we're going to look at the x variable, and I want to sort of cancel out the x's in the second and third equations, right? So that's really looking at this column right here. So let's go ahead and cancel out the x from the second equation first. So in order to do that, I think what I'm going to do is I'm going to take the first equation, I'm going to multiply it by -1, and I'm going to add it to that one, right? Because I see there's a 1 in front of this x and a 1 in front of this x. And so I'll get a -1 plus 1, that'll be 0. That's what I'm trying to do. And then I'm going to do the exact same thing to this row of the matrix. I'm going to multiply the row by -1, and then I'm going to add it to the second row. So let's go ahead and do that. When we do that, the first row stays the same, or the first equation rather. So we get equals 4, and then -1 times x, that's -x plus x, that's 0. That's what we're going for. And then we've got a -y times -1. It's going to be +y plus 2y. That's going to be 3y. And then we get -3z plus -2z, so that's going to be -5z equals -4 plus 10 is going to be 6. And then the last equation stays the same for now. Now, if we look at the matrix, the first row stays the same. We're not changing that one. Now, for the second row, we get 1 times -1 is -1, plus 1 is 0. And then we get -1 times -1 is +1, plus 2 is 3. And then -1 times 3 is -3, plus -2 is -5. And then -1 times 4 plus 10 is 6. And we can kind of see that we still get the same numbers, right? We get that 0 and the 0. We get 3 and 3. That checks out. We get -5 and -5. That looks good. And then we've got a 6 and a 6. So the matrix is still reflective. Then let me just fill out the last row, which we didn't change. So they're still mirroring each other, right? We did the same thing to them. Same kind of idea. Okay, so let's go ahead and proceed with our solving. Let's look at the x variable again. I want to cancel out that 3x on the bottom, so I'm going to multiply the top row by -3 and add it to the bottom. And I'm going to do the same thing with the matrix, like so. When we do that, let's see. The first two equations stay the same. And then in the last equation, if you do out the math, I think what you'll find is we get a 0, and then we get -3 times -y is positive 3y, plus -y is going to be 2y. And then I think we also get a minus 4z here. And then if we do -3 times 4 plus 14, I think we end up getting a 2. Okay, and then looking at the matrix, the first two rows stay the same. We're not changing those yet. And then for the last row, let's see, -3 times 1 is -3, plus 3 is 0. -3 times -1 is +3, plus -1 is 2. And then -3 times +3, that's 9, plus 5 is -4. And then -3 times 4, that's -12, plus 14 is 2. Yeah, look at that. Very nice. Okay, let's proceed on with our solving. So now I've canceled out the x's. I'm going to narrow my focus down. I'm looking at these two y's. I want to cancel. I'm going to actually go ahead and before I go ahead and cancel it out, I'm going to notice that in this bottom row here, we have 2y minus 4z equals 2. Those all have a factor of 2 in them. So I'm going to divide out by a factor of 2. It'll make the arithmetic a little bit nicer. And I'm also going to do the same thing to the bottom row of the matrix, right? So if we do that, we get x minus y plus 3z equals 4, 0 plus 3y minus 5z equals 6. And then we get 0 minus y minus, or sorry, not minus y, plus y minus 2z, it's 4 divided by 2, equals 1. And then the matrix, we get the same thing, the first two rows. 0, 3, -5, 6, and then we get 0. 2 divided by 2 is 1. -4 divided by 2 is -2, and a 1 again. All right. And now I can go ahead and cancel out some y's. So I'm going to go ahead and cancel out the top y because all I have to do that is I just have to multiply this by -3 and add it to that one. It's a little bit easier than multiplying things by 1/3. So if we do that to the matrix and the system, first equation stays the same. Then we're going to get a 0, and then we get y times -3 is -3y plus 3y, that's going to be 0. And then we get -3 times -2z plus -5z. I think we end up getting just a plus z. And then for the constant coefficient, -3 times 1 is -3 plus 6, it's going to be 3. And then this last equation stays the same. And then for the matrix, the same sort of arithmetic applies as we've seen. So we can see that the matrix already, we know it's going to be 0, 0, 1, 3 from the work we just did. 0, 1, -2, 1. Okay. And to sort of get this into a nicer form so that we can do our like back substitution and everything, I'm going to go ahead and swap these two. And correspondingly, I'm going to swap the two rows of the matrix. So when we do that, we get x minus y plus 3z, that's a bad z. Here we go, equals 4. And then we write 0 plus y minus 2z equals 1. And then we've got 0 plus z equals 3. And then correspondingly, matrix, we get 1, -1, 3, 4. We swap these two rows. So now we have 0, 1, -2, 1, and 0, 0, 1, 3. Excellent. So now you notice that we can back substitute, right? If we just kind of looked at this system that we have here, we've got z equals 3, and then we can substitute that into this line. And then whatever we find for y, we can substitute y and z into this one, and we can figure out what the solution is. It's good to note that in the matrix, what this looks like when you're ready to back substitute is you've got a 1, 1, 1, and zeros underneath all those leading ones. So you can see that like the system of equations and the matrix, they mirror each other in this way. Now, let's make a note about this. So, well, real quick, let me write down. Now we can back substitute. And if you want to see more work on back substitution, I recommend you watch previous videos. So now let's make the note. So there's a note here that the moves that we did to produce an equivalent system for linear systems, right? So like adding equations together or multiplying them by some constant, that kind of thing. We did the exact same thing to the matrix, right? But when we do them to matrices, they're what are called elementary row operations. So let's write that down. The moves that produce an equivalent system for linear systems those are called elementary row operations. Which is usually abbreviated to EROs, because it's a lot of syllables to write out every time. So they're called elementary row operations when doing them to matrices. Okay, let's make a list of these elementary row operations just so we're all on the same page about what exactly they are. So the first one is adding a multiple of one row to another. The second is multiplying a row by a non-zero constant. And lastly, we can also swap rows, as we saw in the previous example. So all three of these are elementary operations. They're all very good tools for solving systems using matrices. Okay. Let's talk about some other matrix properties, because we'll need to know some words before we can actually write down the process for solving the system with the matrix. So here's another note. So I'm going to go ahead and define what's called row echelon form for a matrix. It's a little bit of a long definition, but I'll do some examples as soon as I'm done writing it down so we can get sort of a grasp on it. So when a matrix has leading ones in all non-zero rows and the leading ones are in a sort of cascade pattern. So what I mean by that is, so if you're in a row and you move down to the next row, the next leading one will be on the right. So if you move down a row, the next one so if the leading ones are in a sort of a cascade pattern and there are all zeros underneath the leading ones, the matrix is in row echelon form. So let's look at some maybe examples. So if I had a matrix that maybe looked like 1, 2, 3, 4, maybe, and then like 0, 0, 1, 3, and maybe like a 0, 0, 0, 0, we can see that, okay, each row, they've got a 1 leading on the left. They are in a cascade pattern. So if we started with the one up in the top left here, we move down to the next row. The next one is indeed to the right. So it's sort of in that cascade pattern. And underneath the leading ones, there's all zeros. This is in row echelon form. Sure, the last row is all zeros, but that's okay. We only need leading ones in all the non-zero rows. So this is in row echelon form. The row echelon form is usually abbreviated as REF for the same sort of reason that we abbreviate elementary row operations as ERO. Okay, maybe something that's not REF is maybe like 1, 4, 2, 0, 1, 0, 3, 0, 1. This is not in row echelon form because, well, for several reasons. This leading one here, it doesn't have all zeros underneath it. There's that 3 there, so that breaks. And in addition, if we looked at this leading one, it has, it's not leading, right? There's a 3 in front of it. It's not just all zeros. So this 3 is really bad. So this is not REF. Okay, maybe another example of something that's not in row echelon form. Let's do something a little bit smaller. Let's do like 1, 2, 3, 0, and maybe 0, 0, 1/2, 4. All right, this is not in row echelon form because of this 1/2, right? It's the leading number of that row, but it's not 1. We need it to be 1. So this is not in row echelon form. And then just maybe one more example of what something in row echelon form looks like. If we had 1, 0, 0, and maybe 0, 1, 2, and then 0, 0, 1, this is indeed in row echelon form because we've got leading ones, which all have zeros underneath them. And they are indeed in a cascade pattern. So this is in row echelon form. Okay. So another quick definition, if we also have only zeros above the leading ones, then the matrix is in what's called reduced row echelon form. So, for example, if we had a matrix that looked like 1, 0, 4, 0, 1, 2, 0, 0, 0, we can see that this is in row echelon form because we got those leading ones. They're in that cascade pattern. There's zeros below them, but there's also only zeros above them. There's no other numbers above them, just 0. So this is in reduced row echelon form, which is usually abbreviated as RREF. Something that wouldn't be in, or actually, before we do that, another example of something in row echelon form may be 1, 0, 2, 0, 0, 0, 0, 1, 0, 0, 0, 0, maybe. This is in reduced row echelon form because we've got, here are leading ones. They're indeed 1, they're indeed leading. They've got zeros below them. They are in that cascade pattern. So it is at least in row echelon form, but also there's only zeros above them. So this is in reduced row echelon form. Something that wouldn't be reduced row echelon form would be, for example, this one right here. It's in row echelon form, but the problem is that it's got that 2 above this leading one. So this is not in reduced row echelon form. It's only row echelon form. Okay. So now that we know what those words mean, let's go ahead and write out the steps to solving a system of linear equations with a matrix. So first off, you're going to go ahead and write your system as an augmented matrix. Step 2 is you're going to perform elementary row operations to write the matrix in row echelon form or reduced row echelon form. Reduced row echelon form is a little bit better, and we'll see why in a sec. And 3, you want to translate your matrix back into a system of linear equations. And then, of course, back substitute as necessary. So those are those steps. This video is already pretty long, so I'm going to go ahead and cut it off here. But in part 2, I'm going to go ahead and talk about some examples of doing this. So if you want to see these steps in action, you should check out that video.